Okay, so this is part 2 of the series where we've taken this image of what I assume to be human red blood cells off the internet, and we have, we are going to segment, detect the red blood cells, and then quantify some characteristics of those red blood cells, such as their size, the average size perhaps, and how many there are of them. So in part 1, we acquired the data, we loaded it into Python, and we began our image segmentation. And we used an Otsu threshold on a grayscaled image of the red blood cells to separate background pixels from foreground pixels, which are our cells. So here I'm just going to briefly talk about what the next steps are now and what our general pipeline for analyzing this image is going to be. So first step was to acquire the data. We got it from the internet, but in the future you will probably get it from a microscope. Once you have your data, you need to segment your image. You need to separate background pixels from foreground pixels, which are what you're interested in, which are cells, nuclei, some sort of structure in your tissue. In our case with these red blood cells, I decided that we do an Otsu threshold, which seemed to work quite nicely. However, there were some issues with our Otsu threshold where we have what appears to be holes in some cells. We have what cells have segmented and they kind of look like donuts, maybe like horseshoes in some instances. So we need to try and deal with that, and that's what we're going to deal with in this video. But once we've dealt with those issues and we have our cells segmented quite nicely, we're going to go on to detect each cell, each object, and the way we do that is that an object is described as pixels that are associated spatially, i.e. pixels that are connected to each other, they are touching. And when we have sufficient enough pixels touching, we will call that an object when it passes a certain threshold size. And there are tools that are easily implemented in Python to detect those objects. And then from there, we can start doing our quantification. We can describe those objects. We can determine the average size in pixels of those objects, or other characteristics. There are many. And then from there, we can just do some basic statistics, like summary statistics, describing our data. You know, do we have a normal distribution of the sizes? Or is our data kind of biphasic? Do we have different cell types there which are of different sizes? This kind of stuff. We can start exploring the data, and ultimately we can determine how many red blood cells we have. So that's the general pipeline. We have done acquired data, and we've done our segmentation, but we need to do some processing, and we're going to use mathematical morphological operations to do this. So just to recap what we did in the last video, we imported imread from skimage, and we're using pyplot and matplotlib to visualize each step of our image analysis pipeline. So I'm just going to import those in. I have my image saved here. You have it wherever you saved it. Let's have a look. This is the original image. We first grayscaled and we picked an arbitrary channel. I think we used the red channel, and then this is our grayscaled image. From there, we had a look at the histogram of the grayscaled image, and we saw that there was 2 clear peaks of intensity values. We determined that this was these darker intensity values were our cells, our red blood cells, and the brighter and more numerous pixels were associated with the background. So we have a foreground, a background, and what the Otsu threshold, and then we did an Otsu threshold, and what that did was it determined the optimum point to separate these pixels, and we made all these 1 below the separation point and all these 0 from our threshold point. So that's what we did. Let's just import the Otsu Threshold from skimage.filters, and we're going to do the threshold here. Well, we're going to determines what the pixel intensity value that will be our threshold, and it's 152. We're going to apply it to our grayscaled image, and then we're going to have a look at it. And yes, we've done it. And so this is where we got to in the last video. And what you see is the issue I was talking about earlier. We have this kind of donut shape in this cell here, and the reason for this is when we look at our original image, the red blood cells have that very classical concave shape to them, which increases their surface area for oxygen transport. But the reason, the issue with that shape is that our Otsu threshold assumed that it was background pixels because it was brighter. Its intensity value was brighter than our Otsu threshold that was determined to be at 152. So we have this donut shape. Oh, and we got it here. But then there's also other instances where we have this kind of horseshoe shape. So what's happened here is that, well, the image was just, because of the way it was threshold with the Otsu, is that the perimeter wasn't connected, unfortunately. We're going to try and deal with that by doing an image closing. I'm going to close the image. And yeah, we have a lot of the donut shapes mainly. Oh, here's another horseshoe. So that's what we're going to do first. So the first stop, actually the first thing we can do is, when we have this donut shape, we can just do something, we can just fill it in. So we have the perimeter, and everything within the perimeter, we can just turn it to a 1. So then we remove the holes in our image, and that's very easily done. So that's what we're going to do first. So to do that, we're going to go from scipy .n dimensional image.morphology, import binary fill holes. Then all we have to do is we need to apply this function on our Otsu image. So to do that, remember with how we're naming files, we're doing image_Otsu filled. So we have a record of what we've done to that data, and just apply the function to the image Otsu. And let's see what happens. So let's run that. We have an array of true or false, similar to what we get from the Otsu threshold function. And let's plot that. So plt.imshow, and then put in image Otsu filled. Cmap. Cmap is going to be great. So let's have a look. And what do we see? So here we had a donut originally, and you can see that it's filled in. So actually, what we have right now isn't that bad. There's a couple of issues. For instance, the horseshoe-shaped cells that I was talking about earlier, nothing's changed there. And the reason is because technically, well, this isn't a hole, is it? It's just that's the if this was closed, this bridge was closed, and then we did the image fill, then we would have a filled object. So we need to use a method that would first connect these two sides, and then we do an image fill. And the way we're going to do that is with image closing. But before we do that, there's a couple of other things with the image that we need to sort out before we start labeling the objects, which is we have a couple of cells where the boundary between them has disappeared or is just non-existent. And we have this kind of like snowman shape. We got it here, got it here. Here we have a, I don't know, quadruple snowman. Here we have a kind of cross. We need to deal with that. Otherwise, when we start quantifying this object, it will be treated as one object with the size, which is approximately 1, 2, 3, 4, 5, 6 times probably the average size of a red blood cell. And that's not good. So we need to try and segment this or split these cells. And we're going to do a watershed, I think, and we'll talk about that in a later video. But before we do that, we need to deal with these horseshoe shaped cells. So to do that, we're going to do an image close. And what an image closing is simply we dilate the image. So wherever we have pixels that equate to 1, what happens with a dilation is they just expand. So each object gets a little bigger. And what we hope will happen when we do that is that this gap between the two sides of the cell will connect. So then we have a donut shape. But the problem of just doing a dilation is that it will cause it will cause cells to become bigger. They will dilate, and that will influence when we measure the size of the cell. So what we need to do then after we dilate the image is we need to erode it, so bring it back to their original size. But because these two sides will be connected, the erosion won't remove that connection, hopefully. So we have made the cells bigger. We've connected all of the perimeters of the cell, but then we erode the image, bringing them back to its its original size. But we've connected these parts. So that's what we're going to do. That's an image closing, and it's a very common image processing technique, and we use it to remove noise. That's what we're going to do now. So the first step is to dilate the image. So we're going to import from skimage.morphology as skimo. And then all we have to do, remember when we label each step, that we have a record of what we've done. So this will be image dilated Otsu. So I'm going to ignore this binary step right now because we're going to first try and close the image. So image dilated Otsu or skimo binary dilation, and then image. We'll put our image Otsu there. Yeah, that looks good to me. And then we're going to close the image. So image closed will and Otsu, because we did an Otsu, will be skimo dot binary erosion. Yeah, because closing an image is a dilation followed by an erosion with the same structure and element. Don't worry about that now. So put in our dilated Otsu there. And then finally, once we close the image, we're going to do the fill. So image filled, but it was first closed, and before that it was Otsu. So the file, the variable names start to get bigger, bigger the further on you go. So that will be binary fill holes and put image, close Otsu. Okay. So I'm going to run all that. It runs fine, but quite a lot of there's three steps there, and I want to visualize each step and compare it against the original image for us to see what we've done. And I've prepared some code earlier to show that. I'm not going to type it out in front of you because you can have a look at your own time. But I'm just going to plot each step onto a figure. So there we go. So here's our original image, unaltered by us in RGB format. Then we have the grayscaled and filled. So what you can see is that it worked quite well, but we have these horseshoe cells here and here. This is the image Otsu Threshold and dilated. So what we did was we expanded each cell in size, and you can see that they're a little bigger compared to these ones. Unfortunately, it didn't resolve our issue with the horseshoe crab here, but I think it solved the issue here on this one. Can you see that there's no black here? So now we have a kind of donut shape, like this one. Now this is the image closed, so it's this image, Otsu thresholded, dilated, and then followed by an erosion. So the nuclei have gone back to their original size, but where the dilation worked to close the object, it remains, and it does here. So it seemed to have worked on some cells, but not all. And then finally, this is the image closed and then filled. So as you can see, almost every single nucleus is filled, except for this one, which has that really big the bridge is too big. There's too many black pixels, so the dilation didn't work, and it wasn't enough to close the cell when we did the closing. So you know what? We're probably not going to get any better than that. One cell out of, I don't know how many is there, 50, 100, is good enough. We can remove that data point later on. We'll remove that cell. So I think now our next steps from here is that, well, we still have a lot of cells which have clumped together because they're just in a close vicinity of each other. So we need to use a method to separate them, and we're going to do a watershed to do that, but we're going to do it in the next video, so I think that's enough for now. But yeah, I think we've definitely improved to what we were left with in the last video.